Welcome. This is ECE 341 Random Processes, Part 1, Lecture 12. In our previous lecture, we introduced the idea of families of random variables. Families are just particular forms of a probability mass function that provide a structure for describing the behavior or understanding the behavior of a random variable. If you have an experiment that you know follows the general form of a particular family, you can use your knowledge of that family to save you some time and immediately jump into a working and useful model for that situation. Having full knowledge of a random variable through its probability mass function or its CDF, both of those have equivalent information, is good, but sometimes it can be cumbersome. These random variable families can have large dimensions, they can be quite complex, and they don't always have immediate access to some of the information that we would like to know. So the probability mass function, whether it's derived from a family or somewhere else, is a complete description of the behavior of a random variable, but it doesn't always give us the information we want or need easily. So we're going to look for some other ways of maybe getting information out of a probability mass function. And one of those things is this idea of a summary statistic. A summary statistic is something that we usually derive from a probability mass function, but it provides us access to some really useful information, something that allows us to draw information about the random process, maybe without having to worry about all the details of the probability mass function. And it allows us to maybe work our way towards better understanding of particular results from an experiment. An example of this might be the following. You take a test, right, and you get your test score back. And on that test, it says something like 50%. It's unlikely that when you get that test back, the first thing on your mind is, boy, I'd like to have access to that full probability mass function so that I can fully understand this random process that is students taking this exam. Instead, you're probably just more interested in how well did you do on the exam? Were you close to the average? Were you above average? Were you below average? What was the variability on the exam? Those kinds of data or those kind of summary statistics provide us that snapshot information that just better helps us understand our exam performance of 50%. So if you ask something like, what was the average on the test? And the test average was said to be 45, for example. That certainly would give you some information. You might feel a little bit of comfort in this idea that you were 5% above average. So while a 50 itself on initial blush, the first time you got that doesn't seem so good, knowing that you did better than average certainly is better than knowing that you did worse than average, right? If we knew something about the variability as well, we would know a little bit better about whether that 5% over average was really significant or not. If the variability within scores was very low, for example, let's say the standard deviation was only like a point, being 5 points above average would mean you were way, way above average. There would be very few people in the class that would likely be having a score higher than yours. If on the other side, the variability within the random variable was quite a bit higher, like the standard deviation was something like maybe 10 or 20 points, your score of 50, only 5 points over the 45, would not be so distinctive, right? It would be more likely that you were kind of in the middle of the pack as far as exam performance. So we're going to try to get an idea more formally of these summary statistics and how to compute them. The way we're going to start is we're going to look at some ideas of averages for a random variable x. And there's lots of different ways we can think about this idea of an average. Here are going to be three of them that we'll start out with. The first one we're going to talk about is this idea of a mode. The mode really is just the most likely value or values of our random variable x. And so we get this information from the probability mass function. The mode value, so x mode, satisfies the following condition, that the probability mass function at that value or values has to be greater than or equal to all other values of the probability mass function. So if I plotted out the probability mass function, we know that that gives us an idea of how likely different values are. We would just look for the peak in that probability mass function or the collection of values that have the same peak value. And any one of those would satisfy this definition of a mode. Oftentimes, modes are kind of in the middle, but there are distributions that have modes off onto one side. We'll show some examples of that coming up here in a minute. One of the maybe disadvantages to this idea of a mode, it does tell us which things are just most likely right out of the bat, right? If you've got 10 values, the mode's going to tell you the one that's most likely to show up, right? One problem with that, though, is that this mode need not be unique. And this lack of uniqueness in this particular form of average or this summary statistic is kind of debilitating. Lack of uniqueness just makes it harder to know how to do subsequent or additional calculations with this. So while people definitely do use mode, it's probably not the preferred way of describing what we might call an average. Another one that we oftentimes see is this idea of a median. Medians are also quite popular, but they are probably not as popular as the last one we'll talk about here in a minute. What is a median? A median can be thought of as maybe that 50% point within the distribution. More mathematically, we could say that the median value satisfies a pair of properties or a pair of conditions. We would say that the probability that a random variable x is less than or equal to the median must be greater than or equal to a half, and simultaneously, the probability of x being greater than or equal to the median, right, also has to be greater than or equal to half. Some sources define median using the strictly less than or strictly greater than rather than the less than an equal or greater than an equal. Um, that's okay. You just need to know what your definition is and use it. It can make a little difference in what the values coming out for median might be. I would also note that much like the mode, the median need not be unique. And the median may not even be a part of the range space of our random variable x. Again, we will take a look at some examples of this and talk a little bit more about how they might be computed and how they compare to the other ones. One comment I would like to make is the special role of a median in certain kinds of distributions. Medians are very resilient to outliers or highly skewed data. So if you take a look at a probability mass function and you see that that is quite skewed, that maybe some of the most common or most likely values are way the heck off on one edge or the other, that kind of skewness can really cause a difference in what is the mean, median, and mode. And the median tends to be not as influenced by some of these really outlier data. As an example of this, a lot of times if you're reading the newspaper about wealth, for example, so a lot of people spend a lot of time talking about wealth, the generation of money, how much wealth Americans are different, age groups within America, what their incomes or their savings or their 401ks look like. And what we find out is that the distributions of wealth in this country are quite skewed. So there's kind of like the ordinary everybody people, and then you got these super mega rich people. Those super mega rich people, even though there's very few of them, have so much money that if you looked at some of the other kind of statistics, they get highly skewed by those super rich people. And as a result, those other forms of averages tend not to be reflective of kind of the common everyday Joe. So in those particular cases, it's very common and quite oftentimes the preferred way to report something like a median, which is more reflective of the guys in the middle, right? Not so much maybe the ones who are the super rich, or also maybe on the other side, the ones who are really struggling and have very little money. So, kind of the takeaway I would do on that is that median is resilient, right, to outliers or skewed distributions. And if you have a situation like that, you might consider using the median as a way of representing what is kind of the value expected for that middle of the pack kind of person. Expected value is probably the one that is most commonly used, and it's certainly the one that we're gonna spend most of the time in this class. It's the one that we are gonna look most at as far as computation and its connection to particular distributions or families of random variables. The expected value is what many people consider as a random variable's average value. So sometimes when people talk averages, that's immediately what they think about is this idea of expected value. We'll see that connection when we look at how to estimate the expected value. The expected value is really a center of mass calculation. It tells us the balance point of a probability mass function. Again, when we get to our examples, we'll see this. If you draw your probability mass function, right, and you think of those mass points sitting around on that real number line, this expected value, the center of mass calculation, would be where you would put your finger underneath that real number line, so that all of those masses, all those probability mass values would end up being balanced, right? So that the thing wouldn't fall over. Again, I'll draw a picture of that in a bit. So how might we define this? The expected value, we're going to use a notation here, capital E, that's red expected value, and then it's the expected value of random variable x. That's one way of doing it. We're going to also look at some other expected values. It doesn't just have to be of x. We could do things like expected value of x squared. You could do expected value of some function of x. Expectation by itself is just a kind of a weighted average of the probability mass values. It's weighted by whatever we are taking the expectation of. So when I look at expected x, right, expectation by itself is always going to be summing over all the values x that make up our range space of x, and we are going to be always having in that px of x. And then whatever we were taking the expectation of, that's the thing that weights those probability mass function values. This particular one, expected x, instead of like expected x squared or expected x cubed or expected of some function of x, is so common that they oftentimes abbreviate or give a shorthand notation for that expected x, and they'll just call it mu of x. Mu of x we could read as the mean of x. Mu of x is unique, at least when it exists, which is almost always the case. Almost all distributions have a mean that exists. There are some kind of quirky ones that you end up finding that the mean doesn't calculate out to a finite value. We're not going to spend too much time on that. Almost always the mean exists, and when it does, it's unique. That uniqueness provides some advantages to the mean value, especially when we want to use that in other types of calculations. We know exactly which value to use then, right? If it's a unique value, you use the one that comes out. If you had one of these other distributions where many values are coming out, you have a little more of a quandary, right? You have to decide which one you should pick. And depending on which one you pick, you might get different results or different conclusions out of that. And that ambiguity is oftentimes kind of a detractor of using some of the other ones. So a couple of notes on this idea of an expected value or the mean. The uniqueness of the mean makes it the usually preferred measure of average. And we would also note that this expected value is also called the mean. So you'll hear that as well. So we can have expected x, some people call it an average, and mean value is another one. Overall, I would say that if you just took an arbitrary distribution, there is no guarantees that the mode or the median or the mean are equal. Although there are distributions for which the mode and the median and the mean all equal one another. That tends to happen when we have a probability mass function that is more symmetric in shape and more unimodal with like maybe more likelihood towards the middle. So in some particular cases, it is possible to get all three. Usually when all three are equal to one another, you don't have these kind of like weird outliers way the heck out. And you usually don't have some sort of weird skew or asymmetry in the underlying distribution. Usually when all three are equal, it's more indicative of a kind of high likelihood in the middle and a symmetric kind of distribution. So one of the things you might do, if you don't really know the family, if you're just collecting empirical data, you might take a look at the mode, the median, and the mean, and see how close they are to one another. If they're all really close, right, that might tell you something as well, just about the underlying distribution symmetry, and maybe perhaps presence of outliers on one side or another. So let's do some quick examples of this, and so we'll see if we can come up with calculations for the mode, median, and mean for a couple random variable cases. I'm going to keep both of these examples that we're going to do here pretty simple. So think about throwing a fair four-sided die, and we'll call that random variable x. We know that a fair four-sided die, right, has a uniform probability mass function, and it's uniform over the values 1, 2, 3, 4. Because there are four values it can take and they're each equally likely, they each have a probability of equal to a quarter. So if I wanted to think about it, I could come up with a probability mass function px of x, recognize that this guy is a uniform, right? So it is a uniform random variable, right? Just because it was fair, and it's equal to 1/4 for x equaling 1, 2, 3, and 4, and it's 0 otherwise, something along those lines. And I can come up with a graphical depiction of this guy as well. So I'll go ahead and draw my axis sitting out here. And I'm going to come out with a value 1, 2, 3, and 4. So these are different values of x going 1, 2, 4, something along those lines. And then I'm going to go ahead and look at the probability mass function. This is that distribution of likelihood across the different values in the range space. The range space is 1, 2, 3, 4. So I'm going to see my 4 different values of the probability mass function at those values. And we'd assume everywhere else it's 0. Something along those lines. And we would just note the height of these guys as being a quarter, something along those lines. So I've come up with this probability mass function, this mathematical model, a complete description that reflects this random variable x, which is throwing this fair four-sided die. From this, I would like to go ahead and figure out what is the mode and the median and the mean of this particular random variable. Let's start out with a mode. So what is x mode equal to? If you remember, x mode says, if we go back up to the conditions on this guy, the mode in this particular case says what? That the probability mass function for the mode is greater than or equal to the probability mass function everywhere else. It's basically the tallest, highest point of probability in our distribution. In this particular case, we see that the top or the highest point of probability in here, right, all looks about the same value, right? All of those guys, 1, 2, 3, and 4, all have the same value. So the probability of 1, right, is greater than or equal to the probability of 2, which is greater than or equal, turns out to be equal to the probability of 3, which is greater than or equal to the probability of 4. All 4 values satisfy the definition of mode. So mode here, right, could be drawn from the set 1, 2, 3, or 4. They are all reflective of the largest value, the highest probability, the highest likelihood for this particular distribution. We had made the comment before that modes do not have to be unique, and we certainly see that in this case. The mode is not unique. The mode is actually every single value in the range space of X. So that's the mode in this case. If I was going to look at the median in this guy, so what is X median, right? What is the median value? If we go back to the definition in here, we look at that median value, right? It says the probability that the random variable X is less than or equal to the median must be greater than or equal to a half, and the probability that X is greater than or equal to the median must be greater than or equal to half. So let me go ahead and take a look at this and see if I can come up with some values that this would be true for too. I'm going to go ahead and do a little color coding here. So we were doing the mode kind of based on that red stuff. Let's go ahead and do some blue now for thinking about that median. What I'm going to do is I'm going to pick some values on the horizontal line. So I'm going to look at everything from 2 to 3, and I'm going to do a little bit of probability calculations. What is the probability, right? Go back up to the definition here where we're talking about things like that median, right? What's the probability of X being less than or equal to that value 2, for example, or greater than or equal to that value 2? So I'm going to go ahead and say, what is the probability that X is less than or equal to 2, for example? If I do that, I know that the probability that X is equal to 2 is a quarter, and there's only one value before it also of a quarter. So the probability that my random variable X is less than or equal to 2 is equal to a half, right? And what is the probability that X is greater than or equal to 2? And we see that that's going to be a quarter plus a quarter plus a quarter, right? 2, 3, and 4 all included in that. And that's going to be 3/4. And both of those are greater than or equal to a half, greater than or equal to a half. Therefore, 2 does satisfy. It satisfies, right? It satisfies this idea of a median. That certainly satisfies the value of the median. And guess what? If we do the same sort of thing for probability that X is less than or equal to 3, right? We know that that is equal to 3/4, which is certainly greater than or equal to a half. And the probability that X is greater than or equal to 3 is equal to a half, which is greater than or equal to half. And so that also, right, satisfies that median. So X equaling 3 satisfies that. And any value in between there does as well. If I put what's the probability that X is less than 2.5, right? That would be equal to half. What is it greater than? It's also equal to a half. Any value in that interval. So my median value here, right? It's all values X such that X is between, whoops, let's make this a little bit spread out, that X is between 2 and 3 inclusive. So again, this is something that does not give a unique value for this particular distribution. Furthermore, some values of X that satisfy the median calculation, right, are also values that do not occur in a range space. So I could say a value of X median equaling 2.5 works, right? 2.5 is not a roll I can get on this die, but it does meet or satisfy this definition of median. So there I don't just get 4 values, I get an uncountably infinite number of values, of which the vast majority, right, do not actually reflect values that I get from rolling that die. If I go ahead and do the mean, right, the expected value, I'm going to take a look at X mean, right? Which is expected x, right? Which we called mu of x. And how did we say that we would get that guy? We said we would sum over the range space, so sum over Sx of x times Px of x. In this case, there are 4 values in the range space, 1, 2, 3, 4. All of them have the same px. So I'm going to get a 1/4 times the value of x, basically, summed up over those 4 values. So I'm going to have a 1 plus 2 plus 3 plus 4 is the expansion of that sum. 4 and 3 is 7, and 2 more is 9, and 1 is 10. So this is going to give me 10/4. Or I get mu x equaling 2.5, right? That mean value is unique as we expected, right? So it's a single value, and anytime I needed to use that particular average, I know exactly when to use. I wouldn't necessarily know which one to use here. I wouldn't necessarily know which one to use here. Here it's absolutely known which one I'm going to use because that guy is a unique value. So in computing this mean, right, we get a unique value. Where is it? It's, whoops, let's make this into something a little bit more fine. So that mean value is sitting right there between 2 and 3, equally distant. So what was this thing about this mean as being a balance point? If I pictured, right, the real number line as being like a piece of wood, right, and I put some weights on there, right, one weight was sitting out here, right, 1.5 units from where I put that mean, one was out a half from that guy, and I did the same stuff on the other side, and all of those weights weighted the same amount, right? This guy, right, would balance. It wouldn't fall over in one direction or it wouldn't fall over in the other direction. It's like I've got a teeter-totter, right? And I'm just finding where the fulcrum of that teeter-totter is so that it just sits there in complete balance. That's what a center of mass calculation does. That's what this expected value of x does. It tells us where if I put my finger, that's this piece right here, right? Where if I put my finger is kind of the fulcrum of this piece. It would not fall over. It would be in balance. Okay, so that's one example of computing out these 3. We'll notice in every single case, not a single one of them gave us the same value. Let's do the same exercise for a slight modification. Let's do this one for a different kind of die, but this die, we're going to call it Y, also 4-sided, but it's one that's weighted where the probability is proportional to Y. We had already taken a look at this kind of situation before. This is something we did in one of our previous ones. So the probability of Y, we know we have 4 values in there. So we have Y equaling 1, Y equaling 2, Y equaling 3, Y equaling 4, and then otherwise, and we know that otherwise is going to be 0 in there. Because it's proportional, I could write these out as CY for the first one, or I could have called it C for the first one, 2C for the second one, 3C for the third one, 4C for the next one. So 10C is all the values, and that has to sum to 1, right? So 10C equals 1, or C equals a tenth. So what I'm going to get in here is 1/10, 2/10, 3/10, and 4/10. So I've skipped a few steps there, but it's one that we've done before. Add them all up, you'll see it sums to 1. Furthermore, you'll see that the actual probabilities themselves are proportional to the value y. I could sketch this thing out as well, so I'm going to go ahead and do that over here. I've got values 1, 2, 3, and 4, so going 1 through 4 on there, those are my values of y. I'm looking at the probability mass functions. Remember, the probability mass function is a complete description. It really tells us all the nitty-gritty details of this underlying process. And I'm going to go 1/10, 2/10, 3/10, and 4/10, something like that. So 0.4, 0.3, 0.2, and 0.1. The first one has 0.1 value, right? The next one has 0.2 value. The next one has 0.3 value, and the last one has 0.4 value. This is a skewed distribution, right? Certainly skewed compared to this other one. This other one kind of just was nice and symmetric about its mean. This guy, right? It has this much greater chance out there towards the 4s and a far less chance out there by the 1s. So it's a very skewed distribution. Let's go ahead and see how all of these different calculations go. Let's look at the mode first. So we're going to look at not x, we're going to look at y. So let's take a look at y mode. Remember, the mode is equal to the value or values that have the highest probability. Clearly, in this particular case, and I think last time when we were looking at modes, we were looking at with a red. So let's go ahead and do that as well. There's our most likely value, right? The one that has the greatest probability is 4 with a probability equaling to 0.4. So what is the mode? The mode is not the probability, it's the value that gives you that most likely probability. So the mode here is equal to 4. In this particular case, the mode is a unique value. It doesn't have to be that way, but it is that way in this particular case. So we do happen to get a case of having the mode being unique. How about the median? The median value of this one in this particular distribution. If you recall, the median value here is that place where you have at least 50% greater than or equal to the point and 50% less than or equal to the point. I'm just going to do kind of an accumulation of probability as I go along here. In fact, this might be a reason why a CDF could be kind of helpful in this particular case. Let's think of a CDF in this case, 1, 2, 3, and 4, right? When I hit 1, I'm going to come up to 10%, so 0.1, right? And then when I hit 2, I'm going to go up 20% from that, which is going to get me to 0.3, right? So I'm going to come up there to 0.3. And when I hit 3, I'm going to add 30% up to that. That's going to be 0.6, something like that, right? And then after that, I'm going to finally get up to, and that's going to be higher than I probably want, but it's going to be up at 1, something like that. That's my CDF. So this median said something about it being like the 50% point. If I look at that 50% point, boy, that seems to be coming in somewhere around that 3 point, right? There's that jump in there. So let's try out that value of 3. Let's take a look at what is the probability that x, right, is greater than or equal to 3. If I go ahead and do that and count it out, 3 has probability of 30%, 4 has probability of 40%, so 0.3 and 0.4 is going to be 0.7. So probability that x is greater than or equal to 3 is 0.7, which is certainly greater than or equal to a half. And then I just look at the other side, the second of the two conditions, is the probability of x being less than or equal to 3, also something that is greater than a half. In this particular case, I'm going to have what? I'm going to have 0.3 plus 0.2 plus 0.1 is 0.6. So I get 0.6, and certainly that is greater than or equal to half. This is the only value in this particular distribution that satisfies both of these guys, right? It satisfies this case where anything above and including that, or anything below and including that, both have probabilities greater than or equal to a half. So the median in this case is also unique. It's going to be 3. And clearly we see that the mode does not equal to the median, right? So we do not get that kind of special condition that we said sometimes can happen where everything's equal. How about the mean? How about the expected value of y, which we said was equal to the mean, right? And we know that that could also be abbreviated mu y, something like that. This is a sum on the range space, right, over all y an element of sy of y times the probability mass function values py of y. Let's go ahead and do that. That is, in this particular case, going to be a sum from 1 to 4. So I'm going to write this as a sum 1 to 4, right, of y times py of y. If I break that up term by term, when y is 1, py is 1/10. When y is 2, py is 2/10. When y is 3, py is 3/10, right? And when y is 4, py is 4/10. So it's just, right, taking those probability mass values and weighting them by the corresponding value y. If I do this, I'm going to get 1/10 plus 4/10 is 5/10 plus 9/10 is 14/10, right? And then I'm going to add to that another 16/10. And so that's going to give me 30/10 if I do all of that. So I get out of that 30 over 10, which happens to be equal to 3. So mu y is equal to 3. That also is the place, right? So if I thought about that with my green pin like we did before, if you put your finger underneath that probability mass function, that's the point where this guy would balance, right? Because this one's so heavy, right? It can be closer to the fulcrum than these guys lighter being further out and still make that thing balance. Oftentimes when you have these kind of skewed distributions, it's not easy to eyeball it, and so you do need to go through the math on that. So in this particular distribution, both or all of the different averages that we look at, mode, median, and mean, all gave us unique values, right? 2 of them happen to be equal, one was not equal in this particular case. Okay, so let's go ahead and move on. Expected values for common random variable families, because those common random variable families have already been derived, we know their form, it doesn't take that much effort to sit there and go ahead and compute out what the means are. What's the advantage of doing this? If you can identify a random variable family as applying to your situation, you not only get like its probability mass function, right? You just write it down, you don't have to derive it. But in almost all cases as well, you will get an expression for what is the mean, and you don't have to go through all the mathematics of trying to compute that mean. These are time savers. We're really, really happy when we know something follows a known probability family, because families have known PMFs and they also have known summary statistics like mean. For a Bernoulli random variable, the mean is just the probability of success P. For a geometric, the mean is going to be 1 over P. For a Poisson random variable, the mean is going to be that Poisson parameter alpha. For a binomial random variable, the mean is going to be NP. For a Pascal random variable, the mean is going to be K by P. All of these are in terms of the parameters that define these families. For a uniform random variable, we're going to get K plus L divided by 2. All of these guys, with the exception of the binomial, have the proof in the book. You can certainly look at it, although we will take a little bit of time and prove at least a couple of them. We can, before we do those proofs, estimate this expected value of x from collected data. So if you know the probability mass function, you can compute it analytically and you can know it exactly. If you don't know a probability mass function, or you don't know the underlying distribution, you can still get an idea of what is the expected value by collecting observations from your experiment, and then you can estimate it with what is called the sample mean. The book uses the notation m sub n. I prefer this one, mu sub x, with a hat on top. So that hat just says an estimate of, and mu of x is what our mean. So an estimate of the mean is equal to what? Well, we're just going to sum up all the values and divide by n. That really, if you remember back to your basic math, is the idea of the average. That's right, the average value x, right? From all those xi's, I going from 1 up to however many observations, in this case n. If we want to get some ideas to why this works as an estimate of the mean, we can do it in the following way. We can look at this mean mn being computed in a slightly different way, but completely equivalent. Still has that 1 over n out front. These different xi's, right, are going to come from the range space. If I look at all the values over the range space, I would just count however many were for a particular value x. So nx is just the number of observations for a particular value x, and I weight that by the value x. These two equations, just draw it out, give you exactly the exact same answer, or the same result. I'm going to take the 1 over n inside, so I can write the sample mean as summing over x, an element of Sx, as to the number of values, right, of a particular x divided by n. So that's the proportion of values that have a particular value x weighted by that value x. This isn't the normal way you'd compute the sample mean. This is the normal way you'd compute the sample mean. But this one provides us some insight as to what's going to happen with this as n goes out to infinity. So we've seen some of this before. That's an idea of relative frequency. If I count the number of times something occurs out of the total number of times, right? We looked at that before, like the probability of some event A, right? You just see how many times A shows up out of n trials, and if you let n go to infinity, you will get that probability of A. So guess what? If I count the number of times x takes on a particular value divided by n, and I let that n go to infinity, that is probability x. So if I do a limit on this whole thing, limit as n goes off to infinity, what do I get? I get this guy down here, right? That's the sample mean in the limit. The sample mean in the limit is going to be just that same sum again, but now instead of what? Instead of this nx by n, we know what that is in the limit. That's p of x. So I just get p of x, and so I'm going to get a sum over all x in the s of in the range space xs. Sx, and then I'm going to be, what am I summing? Well, x times px of x. Well, that is our definition of the mean. So at least as n goes out to infinity, this idea of an average converges to my value expected x. Expected x is a nice estimate. It is something called a consistent estimate. We won't get into the mathematics of that, but it's a good estimate for our expectation. So let's go ahead and do some proofs of a couple means. I've already written these out for the most part because the proofs themselves are kind of tedious, but I'd like to give you an idea of how it works. So let's go ahead and prove the geometric random variable. If you go back to our previous one, we had done the geometric right here, and we said that its mean was 1 by p. Let's just see if that's true or not. Because it's a geometric, we know what its probability mass function is, right? That's given. That's part of knowing a named distribution. And the mean is what? It is a sum over the range space, and the range space here is 1 off to infinity. So I'm going to sum from 1 off to infinity, right, of x times p of x. So that's a sum from 1 to infinity of x times, what is p of x? It's q to the x minus 1 times p. So I go ahead and put that in there as well. I can pull the p out, right? Because that's not a function of the sum variable. And I'm left with a sum, x going from 1 to infinity, of xq raised to the x minus 1. There is a math fact back in Appendix B. You'll find all sorts of interesting math facts back there. And one of them is that a sum from 1 to infinity of x times q to the x minus 1, at least when q is between 0 and 1, it's a probability, it gives us 1 over 1 minus q squared. So I could certainly use that to my advantage in this case. I can use this result here to do some simplification. But before I just use a math fact, I'd like to prove it. I'd like to show that. So here's how I'm going to do that. I'm going to take both sides of this expression and I'm going to multiply it by 1 minus q squared, right? That gives me this on the left. So I'm going to get 1 minus q squared times that sum. And then on the right side, I would get what? 1 over 1 minus q squared times 1 minus q squared, that just gives me 1, something like that. So I'm going to have this guy go to 1. I'm going to take this 1 minus q squared on the inside. It's not a function of the sum variable x. I can bring it right through that sum sign, no problem. And here I have a sum of a bunch of stuff. I'm going to go ahead and do a change of variable. You might wonder how I know all of this. Well, I know where I'm going, and I've had some experience with this. It takes a little bit of experience and a little bit of playing with these things to do that, but I'm gonna just use my knowledge of where I'm going here. And I'm going to go ahead and make a change in variable here. I'm going to create a new variable, x prime as being equal to x plus 1. That's going to change my limits going from now not 1, but 2, right? Because x was 1 before at the start, so 1 plus 1 is 2. Going out to infinity, x is going to get replaced with what? X plus 1, right? X plus 1 equals x prime. So if I solve that for x, that's going to be x prime minus 1. That's this guy, so that's equivalent to x. I still have the 1 minus q squared, and I have a q, right? And it's going to be raised to the, what was x again? X prime minus 1 minus another 1 would be x prime minus 2, something like that. Why did I do all of this? Why was that somewhere sensible to go? Well, if I look just inside that sum, if I look at that piece and I compare it to some stuff that I know, I can recognize this as a Pascal random variable x prime with the parameter k set equaling to 2. And going from 2 to infinity is just the range space. So we're summing over the range space of a PMF. What do we know about all PMFs when they're summed over the range space? They have to be equal to 1. And that basically finishes out my proof, right? I knew that I needed to do something with this guy sitting out there. I just showed that that guy times 1 minus q squared had to sum to 1. So that whole thing is going to go to 1 by 1 minus q squared, which was the math fact. And what do I know as q? Q is the complementary probability to p, so 1 minus q is p. That gives me p squared. P over p squared is just 1 by p, which is where I wanted to get. Okay, so that's a path of a proof to demonstrate that for the geometric random variable, that its summary statistic of a mean, its expected value of x, is indeed 1 by p. Now, as you might imagine, that wasn't terribly intuitive. It wasn't terribly obvious. It had a lot of steps in it, and it required us to use some other information that we maybe had accessible to us, like this Pascal random variables probability mass function. I don't want to have to go through that every time. So I'm really happy that for, let's say, families of random variables, someone has already done this. I'm going to do one more, and we'll see where this guy gets. So let's do the case for the binomial, which is not given in a proof in the book. I would make the comment before we do that, if you wanted the Poisson, you could show its mean very similar to what we just did for this last case when we were showing the geometric. It's a very similar kind of a process in there. You can check that out in the book. So what am I going to do for this one? I'm going to go ahead and take a look at the binomial case and see if I can prove that. What is the expected value of x for any random variable? You sum over the range space of x times its probability mass function. Because I'm looking at the binomial case, I can go ahead and put in what is the probability mass function for the binomial, and I do it over its range space. Range space for a binomial. Remember the story of the binomial? You have n trials and you're counting how many successes were in it, right? So the range space on that could be anywhere from 0 successes all the way up to all of them, all n having successes. So our range space here is going to go 0 to n. And I want to work with this expression and see if I can get it to equal something and find find out if it's what we think it is. Let's go back to what we said this guy was going to equal. We're working on binomial, and I've given you is this thing being NP. So I'm just going to keep that in mind because this will help us understand at least one strategy in trying to show some of these. If I know the result of where I'm going, it actually is kind of an advantage. So we expect this guy to be equal to NP. That's what we're going to be trying to show here. Okay, so I'm going to work with this a little bit. I'm just going to do some simplification, see if I can do a little bit of expansion. What is this n choose x? Well, that's n factorial over x factorial, n minus x factorial. And you'll notice that I'm changing this 0 to a 1 here. How did I do that? Well, I did that because this was what? This is a probability, right? And I know that probability is greater than or equal to 0. I'm looking in one particular case, I'm looking at the x equaling 0 term, and I have x multiplying that. So I have 0 times something greater than or equal to 0. That's just a 0. This x equaling 0 term doesn't add anything to the sum because it's 0. So I don't really have to include it. Adding 0 into anything doesn't change anything. So I'm going to start it at 1 instead. And part of this is because I know where I'm going on that. Okay, so I have something completely equivalent. I've just expanded out what that n choose x is, and I've noted that the first term in the sum is always 0, so why not get rid of it as far as tracking that in the sum limits. The next thing I'm going to do in here is I'm going to take this x, and let me maybe do this a little bit different. Take this x and I'm going to cancel it with one of those x's in the factorial. That's going to leave me just x minus 1 factorial in the denominator. Everything else in there basically seems the same, and we still have that x equaling 1 in there, something along those lines. What's the next step I'm going to do? And this is kind of key. This is a very common kind of technique. Remember what it is that we said we were trying to get this thing to be equal to. We were trying to get this equal to NP. So I'm going to pull out an NP. So I'm pulling an NP out of that sum. Why do I do that? Because I know this is supposed to be the answer. And that means that that sum, what is left over, should sum to 1. And if we're lucky, we'll recognize this as a sum of some known probability mass function, some families distribution PMF, and we won't have to go through all the nitty-gritty work on there. So how do I pull out an NP? Well, I can grab one of the n's from this. That just leaves an n minus 1 factorial up on top, right? And then I also need to get a p. Well, I had x of them right there, so if I just pull out 1, that leaves x minus 1 in there, something along those lines, and I can pull out that p. So I've made a couple of changes to the interior terms so I can pull out this NP part. I've also highlighted, just because it's not always obvious on the first blush, that this n minus x factorial could be equivalently written as n minus 1 minus x minus 1 factorial. The 1 minus a minus 1 cancel. They're the same thing. It's just a little different way of writing it. Why do I do it that way? I do it that way because n minus 1 factorial over x minus 1 factorial, and then dividing that by n minus 1 minus x minus 1 factorial is exactly our definition of what? N minus 1 choose x minus 1. So I'm just trying to make this observation here because it helps me recognize everything in that red rectangle as being this same piece over here. N choose x. Well, n minus 1 choose x minus 1. And then the rest of the stuff just stays the same. Okay, so what can I do now? I can go ahead and make a couple change of variables. I'm going to let n prime be x, n prime be n minus 1, x prime be x minus 1. You make that change. I'm now going to have a sum on x prime going from 0 to n prime. I'm going to have n prime choose x prime. I'm going to have px prime. And I have 1 minus p to the n prime minus x prime. Well, that's just a binomial PMF, and it's summed over its range space. I know that equals to 1. So even though that kind of looks like a mess, because I recognize it from a known, proven probability mass function, and I know all probability mass functions over the range space sum to 1, I'm finished. And I know that that entire piece, this entire guy here, goes to 1. So I'm going to get 1 times NP, which gives me the result of NP. Part of what let me do this was knowing where I was going to go, right? Pulling that out, and that it made it more likely that everything else in there might be in a form of something I recognize from other probability mass function models. Okay, one more topic before we finish today, and I'm going to go through this fairly quickly because it's not a major one. I'm just going to say that there's some super interesting connections between random variable families, most of which we don't have time to cover. Some are in the book, and I do encourage you to read the book. It's not like we have a really heavy reading assignment in here, but I would like to look in detail at one. I know that previously when we were introducing the idea of probability discrete random variable families. One of the ones that we looked at was this idea of a Poisson distribution. All the other families we looked in there, we had a pretty easy story. I think they fell or followed naturally, one on top of the other. And then the Poisson, I just kind of threw it out there and said, hey, here's the model. Let's make sure it's an actual model, and we'll go from there. This one provides an interesting connection between the idea of a binomial distribution in a limiting process, giving us a Poisson process. So let me just lay out what the proof is. This is also in the book. We're going to look at n Bernoulli trials. What's a Bernoulli trial? Success or failure, right? Except for we're going to define the probability of success in an interesting way. We're going to say the probability of success is going to be alpha over n. So its probability of success is going to change as the number of trials I look at gets bigger, right? As the number of trials gets bigger, the probability of success is going to go down, something along those lines. So if I define a variable kn as the number of successes in those n trials, right, we are going to work forward with this. That's something we've seen before. If you have a fixed number of trials and you're looking at the number of successes, that's a binomial. What we're going to see in this, and so the part that's in red here, is what happens in the limiting process. This whole piece up here is just a binomial distribution. But as I let n go off to infinity, we're going to find out that that binomial goes to a Poisson distribution's probability mass function. So we can connect directly a binomial distribution given a particular relation on its success probability to the Poisson distribution as we let the number of trials go out to infinity. So these are kind of cool. So let's show it. Let's show that this actually works. So we know Kn is binomial, and as a known distribution, I can get its probability mass function straight from the appendix, or what we had introduced last time. It's n choose k of the success probability p, which we said was alpha by n raised to the k, 1 minus alpha n, so 1 minus p, that's the failure probability raised to the n minus k over the range space, 0 to n, something along those lines. If I play with this a little bit, I'm going to look at that p of k when it's non-zero. The n choose k is what? It's going to be n times all the way down to n minus k plus 1 over k factorial. That's just one way of expanding out that n choose k term. I have alpha over n to the k. That's an alpha to the k divided by n to the k. And then I have that 1 minus alpha to the n minus k. So I'm just playing some games on expanding this guy out. This first part that I look at, I might notice the following. I have k terms here, and I've got k terms here. So all of those guys multiplied together could be gotten in this way. I could take a product going from 0 to k minus 1 of n minus that product's indicator I, so n minus I over n. That accounts for the same thing that I have here highlighted in green. I still have, if you want to look at it, my alpha to the k. This is my alpha to the k, right? I still have my k factorial. I still have that k factorial. And then I'm going to take this piece. I have something raised to an n minus k. That's whatever the something is to the n divided by that same something to the k, right? So I'm just going to break that sum exponent into a fraction of exponents in this particular case. All right, so I'm just getting some equivalent but alternately represented forms. And these alternately represented forms are convenient for what's going to happen next, which is what happens in the limit as n goes off to infinity. Let's take a look first at that product term. As n goes out to a number infinity, right? The k here is not going to infinity, so there's a finite number of terms. And n keeps getting huge and huge and huge, and we're taking off very little on that. So essentially what converges there is you're getting a ratio there that keeps getting closer and closer and closer to 1, and you're going to have a finite number of those multiplied together. So they're all converging to 1. They're all getting multiplied together to 1, and they limit to 1. So these little differences, n minus I, as n goes to infinity, the I doesn't matter, and I just end with n over n in the limiting. And so I'm going to get 1 multiplied over k times. That's just 1. So this first thing in the limit goes to 1. That would have been hard to see if we hadn't gotten this alternate form. Furthermore, 1 over 1 minus alpha by n raised to the k, k is just some fixed number. As n gets really big, right, this whole thing becomes basically 0. I'm going to have 1 over 1 raised to the k. That's just 1 as well. So that guy's also going to go away. This thing here is going to go away. This guy here is going to go away. They're both going to be 1, right? The last one in here is probably the only one that would require you, if you just are a little rusty on some of your background mathematics, that in the limit, right? This is all in the limit as n goes to infinity of 1 minus alpha by n raised to the n. So that's different than this other one because we're raising it to that thing we're also taking the limit on. That does go to e to the minus alpha. I'm going to let you look it up. I'm not going to do the proof on that. So in the limit as n goes to infinity of that binomial distribution, what do we get? We saw this first one here went to 1. We saw this one here goes to 1, right? And we see that this thing here goes to e to the minus alpha. And if we do all of that, what do we get? We get alpha to the k, e to the minus alpha over k factorial over k going 0, 1, 2, all the way out to, but we went out to infinity because n went out to infinity. That is the Poisson distribution. So we can see this nice, interesting tight connection between a binomial distribution and a Poisson if we take a limit as the number of trials goes off to infinity and the success probability changes as alpha over n. Notice something. This binomial, right? We knew what its mean value was. We just showed that, NP. If you went back way up here before, right, when we were talking about the means of the different families, if I can find one in here, we can look at Poisson. What does the Poisson values mean? It was alpha. That better be preserved here as well. And if I take a look at it, what is NP? What is NP? Well, if I take a look at what my P was, if I can find that somewhere in here, where did I have that? P equals alpha by n, right? So I would get n times alpha by n. The n's cancel. That goes to alpha, which is exactly what we said was the expected value of Poisson. So kind of an easy way of getting that as well. That's enough for today. We'll pick up on some new topics, trying to work our way to finishing out chapter 3, hopefully soon. Next one I think is going to be functions of random variables. That'll be next time.